Hello everyone, my name is Juan Ignacio Camarotti and I'm a PhD student at the Technical University of Braunschweig in Germany within the GECKO project. Today I would like to briefly introduce to you my current research topic, whose name is Cosimulation Strategies Involving IBRA for the Solution of Multi-Field Problems. The main supervisor for my PhD is Professor Roland Buchner, and the main objectives in my research topic are, first of all, the assessment of the benefits of IBRA solvers in surface coupled problems like FSI, taking into account the higher accuracy and higher continuity in the geometrical description of the geometry. Secondly, the development and assessment of mapping operators between different discretizations, for example, IBRA-FEM and IBRA-MPM. Then the combination of different field solvers by suitable coupling algorithms and effective data transfer approaches, basically for solving a multi-physics problem. And last but not least, the development of field mapping techniques for embedded discretizations. When it comes to solving coupled problems, there exists basically two different approaches. On one hand, the monolithic approach, in which in each time step, all the degrees of freedom for the different subdomains are solved simultaneously. This has the major advantage that this is a very stable and robust formulation, but on the other hand, it has the major drawback that it's very difficult to reuse existing tools or to combine different solving strategies for each domain. On the other hand, in the partition approach, basically both subdomains are solved separately, and the data is exchanged between the solvers in terms of boundary condition, basically what are called mapping operators. This has the major advantage that it allows to reuse existing single field codes for solving multidisciplinary problems. This is basically the cosimulation philosophy. And this gives the possibility to employ the best numerical technique and best discretization for each domain. On the other hand, the partition approach has the drawback that in each time step, in order to satisfy the coupling condition, it's necessary to solve an additional interface problem without deteriorating the solution accuracy. So that's something to bear in mind in partition approaches. Now I would like to draw your attention to the different pillars of cosimulation approaches. So the first pillar is the synchronization between the different solvers, so the coupling algorithm and the strategy. And in this regard, you can differentiate Gauss-Seidel solvers, Jacobi solvers, and the use of convergence accelerators basically for speeding up your simulations. Then the second pillar is the data exchange tool you use to transfer information between the different codes. And the last pillar is the data transfer between the different discretization, for example, mapping techniques. I would like to say that for performing cosimulation, basically we are using the Kratos Cosimulation application, which offers all these tools that I am speaking about. So during the first year of my PhD, I have been working on mapping operators and specifically on motor-based mapping. So in the motor-based mapping, the idea is basically to minimize the L2 norm error between the destination field, which is called phi sub d, and the origin field, which is called phi sub o. So basically, it's a minimization problem, which is stated in this expression. And to find the minimum, you need to derive this functional with respect to the degrees of freedom living in the destination domain. So at the end of the day, basically, you need to solve a linear system of equation, which is stated in this expression, to obtain the mapped degrees of freedom in your destination domain, having as information the origin degrees of freedom. So basically, I have been working on mapping approaches both for 1D domains and 2D domains for solving multi-physics problems. So when it comes to multi-physics problems, one of the most common multi-physics problems is fluid structure interaction, and specifically partition fluid structure interaction. So in an FSI problem, you have your fluid domain and your structure domain, and they are coupled. And the coupling is basically because you need to transfer from the fluid to the structure the forces. These forces will deform the structure, and this deformation has to be transferred back to the fluid so as to reflect in some way the movement of the structure. So in this case, the kinematic and dynamic coupling conditions we need to be satisfied on the wet surface are basically the equality of displacement or speeds and the equality of pressures or normal tractions on the wet surface. And something important is that in order to perform FSI simulations, there are basically two approaches. One approach is the body-fitted approach, which is prone to very large deformations when the structure moves. So in this case, basically, you change the fluid domain to reflect the movement of the structure. And the second approach is the embedded mesh, in which you put your structure in embedded mesh and you solve your FSI problem in this regard. Something important when it comes to FSI problem is that the normal case is that you have different discretizations and the coupling interface. So in this case, you need to develop some kind of data transfer operator in order to be able to transfer the load and displacement between the different subdomains. And this is where the mappers come into place. So basically, using the 1D and 2D mapper I developed, we were able to simulate different benchmarks for FSI, like the FSI mock, which I'm showing here, in which we have a finite element discretization for a fluid and an IBRA discretization for the structure. And we obtain very, very good and very accurate results for this benchmark. Then we analyze another typical benchmark for FSI problems, which is the FSI Turek problem. In this case, we use as well a FM discretization for the fluid domain and an IBRA discretization for the structure. And then we were able as well to simulate three-dimensional problems. And in this case, I'm presenting to you a very famous benchmark, which is called the FSI lead-driven cavity. So in this case as well, we have FM discretization for the fluid and an IBRA discretization for the structure. And we basically use Kirchhoff shell elements for this simulation. And in this case, we were able to obtain as well very accurate results in this simulation. So now I would like to finish my presentation talking about my future outlook for my research. And as I come from an aerospace background, I would like to apply in the end all my research to the CAD integrated aeroelastic analysis of aerospace structures. So for this, you need different ingredients, which we already have, but we need to find a way, which is basically the Cosimulation approach, to combine all these ingredients to be able to perform this kind of simulations. So for this, we need isometric structural elements, which we already have in the Kratos IGA application. We need a fluid solver like Kratos or OpenFoam. Then we need technologies to couple different patches in IGS structures. Then we need mapping operators, which was my work during my first year of my PhD. Then we need the coupling algorithms. Then we need data exchange between the solvers. And okay, basically, these are all the ingredients we need to be able to perform this kind of partition FSI simulation, which is of high interest in the aerospace industry. So this was all my presentation. Thank you very much for your attention. And I hope you find my topic interesting.